Folks, this is Ref Bari, Brown University physics grad student. Welcome to 5 Minutes GRE, where I solve a physics GRE problem in 5 minutes or less. Today we're solving a thermodynamics problem related to diatomic gases. So let's take a look. So here's the problem. We have a box full of diatomic gas molecules. What are diatomic gas molecules? They're just atoms, two atoms that form a gas. Okay, so here's a box of these diatomic gases. And the question is, what is the average energy of this system at a sufficiently high temperature? Okay, you don't know anything else beyond the fact that this is a diatomic gas right here in this box. So how do you solve this problem? The first thing you have to do is think, if I'm being asked for the average energy, what tools do I have? The closest connection to average energy to anything in physics is the Hamiltonian. So we write down the Hamiltonian for the system. Now, the Hamiltonian for the system is going to be comprised of three main facts. It's going to be comprised of a kinetic energy term due to the translational motion of these diatomic gas molecules. It's going to be comprised of a vibrational term due to the vibration of these gas molecules as they shake back and forth. And it's going to be comprised of a rotational energy term due to the fact that these molecules can rotate along this bonding that they have. They can rotate at some angular velocity omega, for instance. Okay, so what does each component of this Hamiltonian look like? Well, the kinetic energy term of the Hamiltonian can be just modeled using half mv squared. So we can write p squared over 2m. But remember, this problem is in not one, not two, but three dimensions, meaning that we're going to have three contributions to the kinetic energy term of the Hamiltonian. One in the x, one in the y, and one in the z direction. Now, what about the vibrational component of the Hamiltonian? How do we model that? Well, the spring, well, I gave it away just by saying it, but the diatomic molecule behaves kind of like a spring as it vibrates back and forth. So we can take inspiration from a spring potential energy and model this as follows: 1/2 ks squared. Okay, where s is the separation between the two diatomic molecules, and k is a kind of spring-like constant that simulates how these two atoms vibrate. The last component of our Hamiltonian is the rotational component. Okay, what's that going to look like? That's going to be, as always, whenever we have a rotational component, it looks like this: the angular momentum squared divided by the moment of inertia of the system. But we're not going to have one rotational component. No, we will have two. Why two? Why not three? Because we're in three dimensions. Well, it's because of the following reason. If I draw my rotor or my diatomic molecule in three dimensions, what do I notice? Well, I notice that it can rotate along this axis, right? This is the bonding axis of my diatomic molecule. Now, along this axis, there is no moment of inertia, right? This is the axis that this thing rotates around. So there's only two axes that we consider for the moment of inertia. This is the first axis that this diatomic molecule can rotate around, okay? And this is the second axis that it can rotate around. Okay, so let's say that this is the z-axis, so there's going to be some omega z or L sub z, and this is the x-axis, there's going to be some omega x or L sub x. And that's exactly what you see here. A rotational contribution from the L sub x component and a rotational contribution from the L sub z component. Right, so how is this going to help us calculate the average energy of this diatomic gas? Well, now we apply the equipartition theorem, which says that each quadratic degree of freedom of the system contributes 1/2 kT to the average energy. So this quadratic degree of freedom contributes 1/2 kT, this contributes 1/2 kT, this contributes 1/2 kT, and so on and so forth. We have how many quadratic terms in our Hamiltonian? We have 1, 2, 3, 4, 5, 6, 7. Why are they quadratic degrees of freedom? Because, well, All of them are squared, right? None of them are linear or even constant. So that means the average energy of our system is none other than 7 times 1/2 kT, or 7/2 kT. And that is how you solve this physics GRE problem. Thank you for watching this episode of Physics GRE.